Back in 2023, financial institutions projected that artificial intelligence would replace hundreds of millions of jobs, with software engineering supposedly first on the chopping block. Fast forward to 2026, and 85% of developers do indeed rely on AI for their daily coding tasks. But that massive spike in code generation has triggered a widespread operational failure known as the productivity paradox. AI acts as a relentless amplifier for writing syntax, but those rapid gains in drafting speed are driving severe failures in system stability and downstream quality assurance. This chart shows the exact cost of that speed, comparing the average number of issues found in human-only pull requests versus AI-augmented ones. A pull request is a method of submitting proposed changes to a software project, so others can review the code before it becomes permanent. While developers are submitting 20% more of these requests year over year, the number of fundamental mistakes requiring manual fixes has surged from 6.45 to 10.83, a nearly 68% increase in errors per submission. Because AI creates code that looks syntactically flawless on the surface, reviewers easily miss the embedded logic flaws. As a result, teams using AI multiple times a day now spend an average of 7.6 hours hunting down and resolving the critical production outages caused by those hidden hallucinations. The barrier to writing functional lines of code has dropped to zero. The scarcest resource in the technology sector is no longer the programmer who types the script, but the highly skilled architect who possesses the judgment to determine if that machine-generated output is safe enough to touch a live system. Autonomous coding tools perform exceptionally well when asked to build a small, isolated script from scratch. Put that same AI inside a 20-year-old enterprise codebase containing millions of lines of highly interdependent logic, and the system breaks down. The root cause of this breakdown is a physical constraint in the AI's cognitive architecture, leading to a failure mode called Lossy Compaction. Lossy compaction happens when an AI reaches the physical limit of its short-term memory and begins silently deleting the oldest information to make room for new data. Large language models operate within rigid, finite context windows, which limits how much raw text they can process at one time. When tasked with analyzing decades of accumulated architectural mappings and trade-off decisions, an AI will quickly overflow its limits, forcing the model to aggressively compress 132,000 tokens down to a mere 2,300 tokens just to keep functioning. As it compresses that memory, the algorithm silently drops vital system concepts without flashing a warning. It routinely deletes historically necessary workarounds engineered by senior staff to handle highly specific edge cases, simply because those older solutions don't align with modern, generalized best practices. Without genuine architectural memory, the AI eagerly cleans legacy code by ripping out the load-bearing pillars of the system. This introduces invisible failures under production loads, forcing developers to abandon creative design and become forensic auditors searching for the missing pieces. The accessibility of these tools has convinced many non-technical founders that software engineering is a solved problem. It is dangerously easy to spend 18 months and $47,000 using AI assistants to build a working prototype that functions perfectly for 10 concurrent users. But when that same application attempts to scale to 10,000 users, the illusion of correctness shatters. The AI might generate an authentication endpoint that works in isolation, but entirely fail to implement connection pooling. Connection pooling maintains a small number of open database connections that multiple users can share, rather than opening a new one every time. Lacking this essential guardrail, the AI-generated code opens a unique database connection for every incoming web request, instantly overwhelming the server cluster and crashing the entire application. Beyond structural collapses, there is a temporal mismatch between AI training cycles and live cyber threats. Because these models learn from vast historical repositories, they frequently pull from outdated libraries, eagerly hard-coding deprecated vulnerabilities, like the notorious Log4Shell exploit, directly into new features. Log4Shell is a critical security flaw in a widely used logging tool that allows attackers to take complete remote control of a computer system. When an AI confidently suggests an unlicensed block of proprietary logic or a nested dependency harboring hidden flaws, it destroys traceability. A single compromised dependency merged by an AI assistant without rigorous oversight can cascade across thousands of enterprise environments, mirroring the catastrophic scale of the SolarWinds breach. To survive this influx of chaotic, unstandardized code, organizations are forced to invest heavily in specialized human experts. Engineers are the required glue, writing the highly specific integration layers and security validations needed to keep these automated systems from tearing themselves apart. Relying entirely on autonomous agents also strips organizations of their intellectual property rights. Under United States copyright law, human authorship is explicitly required. If an AI builds a highly complex analytics engine without significant human creative input, that code immediately falls into the public domain, meaning no enterprise can claim exclusive commercial rights to it. Because developers cannot easily trace the training lineage of an AI's output, the black box nature of these models introduces immense legal liability. If an AI perfectly recreates substantial portions of a proprietary codebase, the company deploying that code is exposed to immediate infringement lawsuits. This combination of operational and legal fragility has created a massive disparity within engineering teams. Artificial intelligence effectively acts as a tireless, incredibly fast, but dangerously overconfident junior developer, executing endless boilerplate tasks. Senior developers leverage their hard-won intuition to instantly spot when the machine's output looks visually correct but is functionally broken. Conversely, junior staff, lacking that deep architectural muscle memory, frequently find themselves paralyzed by subtle algorithmic logic failures, inadvertently merging critical vulnerabilities into live environments. By using machines to automate the exact tier of mundane, repetitive work that historically served as the training ground for beginners, the industry has removed the learning ladder. This dynamic turns the entry level into a walled garden, destroying the mechanism through which the software sector produces its future senior engineers. Consequently, the highest value skills for a technical professional in 2026 have shifted away from raw syntax memorization. True enterprise value now lies in domains where the algorithm completely fails, executing complex system design, interpreting ambiguous stakeholder desires, and navigating the shifting budgets and cultural nuances of corporate politics. The artificial intelligence engine has successfully commoditized the mechanical act of writing code, but translating that raw syntax into a secure, legally compliant, and highly scalable business reality remains a strictly human imperative.